All right, here is part 2 of multiplying polynomials. So in the first part, we learned how to multiply basically two monomials or two terms together, where we multiply the coefficients together, and then when we multiply the powers together, we actually add the exponents, right? We're going to use that a lot today as we multiply polynomials together. It's kind of like a matching game. We have to distribute everything in the first polynomial and multiply by everything in the second polynomial, and then see what like terms we have that can be combined at the end. So one way that we're going to do that is a nice visual arrangement that I call the box method, also known as just the area model. So we're going to use the area model to multiply any two polynomials together, and it's just going to help us just kind of organize our thoughts. So the number of terms in the polynomials is going to help determine the dimensions of this area model that we're going to use. So when we say that we're multiplying a binomial times a binomial, that means that we're multiplying two terms times two terms. So there's going to be a 2 by 2 rectangle that creates, I guess, 4 boxes. If we're multiplying a binomial times a trinomial, we know that binomial has 2 terms, trinomial has 3 terms, so we draw a 2 by 3 rectangle. Something that would look like this with 2 rows and 3 columns. That 2 by 2 rectangle would just be like a square that has 2 rows and 2 columns. In the last one, if we have a trinomial times a trinomial, keep in mind trinomials have 3 parts in that trinomial. So we would need to draw a 3 by 3 rectangle, which gets to be really big. It has 3 rows and 3 columns. And these end up being basically like multiplication tables that we have to multiply to figure out what's all on the inside, because that's how we get our area. So let's look at how this works. We're just going to look at some examples here. So in the first example, we're multiplying, the first polynomial is 3n plus 2, and the second polynomial is n plus 3. We're multiplying these two things together. To do this, like I said, you first have to figure out how many terms are in each polynomial, and the terms are separated by pluses and minuses, okay, or the plus or the minus begins the next term. So we have 2 parts or 2 terms in the first polynomial, and then we have 2 parts or 2 terms in the second polynomial. So we are going to use a 2 by 2 box. So that's 2 rows and 2 columns. And the way that we want to organize this is we take one polynomial. I like to start with the first one, and you place each term on its own row. So since the first term was 3n, I put that on the first row, the top row. And since the second term was a positive 2, I put that on the bottom row. Then I'm going to do the same thing with the second polynomial, but I need to put that across the top. Notice there's 2 different lengths that make up the total length across the top of this rectangle. So I split up my binomial into the 2 terms. I had n, which is like 1n, and then I had a positive 3. So n plus 3 is the length across the top. 3n plus 2 is the length down the side. And if we want to figure out what does this equal when we multiply these two things together, we basically just find the area of a rectangle, length times width, to model this. So we're going to multiply. In this first box, think about what row and what column that's in. So what are the labels on the upper side and the left-hand side? That's what we need to multiply to figure out what it equals. So we're going to take 3n times 1n in that box. Now, I write it out that way, but what I really want to do is just kind of do that work either on the side or in my head, because I want to put my answer there. Okay, so eventually I'm going to erase that and put my answer there. Remember multiplying in the first video? You multiply the coefficients, 3 times 1, and you multiply the n's, n times n is n squared. So this is going to become 3n squared. So positive 3n squared is the area of that first upper left-hand corner of the area model. Let's move to the upper right-hand corner below the 3 and think about what the lengths and widths of that rectangle is. It has a length of 3 and a width or height of 3n. So I have to multiply 3 times 3n in this box, which would look like this. That's how I want you to visualize it. 3 times 3n. Now, 3 times 3, those are just coefficients. So 3 times 3 is 9. So 3 times 3n is 9n. And that's positive. I'm going to go ahead and put a plus sign there, and you'll see why in just a little bit. Let's move to the bottom row. On the left-hand side, if I want to figure out what goes inside this box on the left-hand side, look at the row and the column that it's in. Okay, it's in the positive 2 row, and it's in the n column, or the 1n column. So I'm multiplying 2 times 1n inside that box. Well, 2 times 1 is just 2, so that's going to be 2n. And finally, in the last box, I'm multiplying. It's below the 3, and it's across from the 2, so the length times width is 3 times 2, which is positive 6. Oops, I forgot to put the positive on the 2n. So if we want to find the answer to this problem that we're working on, we're multiplying a length times a width broken into smaller parts, smaller areas. All we have to do is take all these individual areas on the inside and show what it would look like as a total sum. So I take the first area plus the second area plus the third area plus the fourth area. Since I have 4 miniature areas, I put them all on a list. Now I'm looking for like terms and writing my answer in standard form. I see that I have 2 terms that have n to the first power, so I can add those together. 9n plus 2n is 11n, and everything else is going to stay the same. Just bring it straight down. And I notice that my answer is already in standard form, where I have the largest power of the variable first, and then it decreases beyond that. So it's like n to the second power, n to the first power, and then that last term where it just says 6, it's like n to the power of 0 because there's not any n's there. So that would be my final answer. That's the result of 3n plus 2 multiplied by n plus 3 equals 3n squared plus 11n plus 6. It's the total area within this rectangular model. Let's see how that works again. Let's try one more. So I notice that I have 2 terms in each one of these parentheses. Each polynomial is a binomial. My first one has 2x and minus 3. So I'm going to put 2x on the first row, minus 3 on the second row. It's important that you put those on the same side. My other binomial has 3x and plus 3. I'm going to put 3x on the top column and positive 3 on the second column. Now I need to start multiplying length times width to get the areas inside these boxes. So in this first box, I need to take 3x times 2x. Well, 3 times 2 is 6, and x times x is x squared. So that's 6x squared. In the second box, so I work left to right. In the next box, I am going to take the 3 times the 2x. Well, let's see. I can do 3 times 2. That's 6. So 3 times 2x is 6x. That one's positive, so I use a plus sign. Let's go to the bottom row on the left-hand side. What should we multiply together there? Well, if you said negative 3 times 3x, because that's the row and the column that that box is in, like a multiplication table. All right, so let's go over here. We have, a negative times a positive is a negative number. 3 times 3 is 9. So negative 3 times 3x is negative 9x. All right, our last box, think about what should be multiplied to get our product in there. What is the area of that? Well, let's see, the row, it's a negative 3. And for the column, it's positive 3. And for area, I multiply because I want to find length times width of that box. And that's just going to be negative 9. So I have 6x squared plus positive 6x plus negative 9x. I'm just going to write that as minus 9x. And then minus 9. You'll notice the way that I rolled it out with the pluses and minuses, I literally can just drag those straight down and put them all in one row, one line across, rather than having to worry about signs or anything. And now it's just looking for like terms. I see that again, I have two terms right in the middle that are x to the first powers. So I can combine them using my rules of adding or combining like terms that I want to combine the coefficients. So 6 minus 9 is negative 3. So I'm still going to have 6x squared at the beginning. My like terms added up to negative 3x, and then I still have minus 9 at the end. So my answer is written in standard form, and they have all the like terms combined. So 6x squared minus 3x minus 9 is the product of 2x minus 3 times 3x plus 3. I would encourage you at this time to try number 3 on your own. Pause the video, and when you're ready, press play to check your answer. All right, so we have to make a 2 by 2 box again, because we see our first binomial has two parts to it, 8b and then minus 1. The second polynomial again has two parts, so it's a binomial, 5b and minus 5. And then we have to multiply on the inside. That first box, I want to do 5b times 8b. I know 5 times 8 is 40, and b times b is b squared, so that's 40b squared. Upper right-hand corner, I have negative 5 times 8b. And this time I know a negative times a positive is a negative. 5 times 8 is 40. And I only had one of the b's. So negative 40b when I multiply those two together to get that area. I move to the bottom left, bottom row on the left-hand side. I'm multiplying negative 1 times 5b. That's the length times the width of that box. So that's going to have an area of negative 1 times 5 is 5. And the b just comes along with it. Finally, in the last box, I'm multiplying negative 1 times negative 5, which is positive 5. So my total area, so when I take all four of the individual areas and add them together. Again, I'm not going to write it as plus negative 40b. I know that's the same as minus 40b. On the bottom row, it'd be like adding a negative 5b and then adding 5. And look at that. My like terms again are right in the middle. So my final answer, my area would be 40b squared minus, when I combine these two, I get negative 45b and then plus 5. All right. Not too bad. It's all those little things put together. Multiplying monomials together like we did up here to get the individual areas. And then it's a matter of just combining like terms, write your answer in standard form. We have our answer. Let's look at last problem. Kind of a big one. In this one, you'll notice there's a lot more to it. There's a lot more parts to it. In the first polynomial, we have just two parts, 4a plus 2, so 1, 2. And in the second polynomial, we have 1, 2, 3 parts, or 3 terms. So that's a binomial multiplied by a trinomial. I need to make a 2 by 3 rectangular arrangement. So I can make it a little bit longer. So on my side over here, where I have just 2 parts, the height, I'm going to put my binomial terms. So 4a and positive 2. Across the top, where I have 3 lengths, I'm going to put my trinomial. The first term goes on the first length, the second term goes on the second length, and the last term goes at the end. So it still has a total length of 6a squared minus 1a plus 2. Now it's time to do, it looks like 1, 2, 3, 4, 5, 6 multiplications because I have 6 empty boxes there. And let's just start on the top row and we'll work left to right. So top left-hand corner, it looks like I should be multiplying 6a squared times 4a. Well, let's see, 6 times 4 is 24. And a squared times another a is a cubed. Remember, if you rolled it out, it'd be a times a again. So a to the third power. All right, middle top row. So I keep moving left to right. I have negative 1a multiplied by 4a. It's the length and the width of that box. In other words, it's the row and the column that it belongs to, like a multiplication table. So I'm multiplying a negative times a positive is a negative. 1 times 4 is 4. And a times a is a squared. All right, last box on the top. I have positive 2 multiplied by 4a. Let's see, a positive times a positive is a positive. 2 times 4 is 8. And I just bring the a along with it. All right, moving to the bottom row. I'm now multiplying 2 times everything in green. So I have 2 multiplied by 6a squared in the bottom left-hand corner. Well, a positive times a positive is a positive. 2 times 6 is 12. And it looks like I just have a squared in there. Just bring that with. All right, moving down. Bottom middle. I'm going to take 2 multiplied by negative 1a. Let me rewrite that. I'd like to get this color-coded. Negative 1a. There we go. So a positive times a negative is a negative. And 2 times 1a is 2a. So 2 times negative 1a is negative 2a. And last box. We're multiplying 2 times 2. Both the row and the column were 2's. So we just do 2 times 2 and get positive 4. So we have all of our individual areas. Now it's time to write it out to find a total sum for the total area. Keeping in mind, I want to write my answer in standard form. So I want to try to reorganize these if I have to with the largest, or the term with the largest exponent first. So that's going to be my 24a to the third power. I'm going to cross them out as I go. That's the only a to the third power that I have. Now I have some a squareds, so I'm going to put those next. Negative 4a squared plus 12a squared. And then the next would be a to the first power, so that's 8a and minus 2a. And then finally I have the plus 4. All right, so we had a few like terms. So as I went through that list, I know that I had a couple of them that were the same variable and exponent. Like I have a couple different a squareds here. I combine my like terms. So this time I'm adding the coefficients and leaving them as a squareds. So negative 4 plus 12 is positive 8. A squared. Then I have, let's see, I have a couple of terms that are like a to the first powers. So 8 subtract 2 is 6. So that's going to be positive 6a. And then I only have one constant term there at the end, the 4. So this time, 4 different types of terms. I have a to the third powers, a to the second powers, a to the first powers, and my constant term is like a to the power of zeros. Everything's in standard form. They're all lined up from biggest power down to smallest power. That's my answer. That's a big problem. All right, that's a really tough problem. If you can do that one, you can do any of these.